Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at expansions with surds. So we're going to look at expanding brackets that have surds in them. So the first use of this is in rationalizing the denominator. So what does that mean? Well, here is a fraction. Denominator is what's on the bottom. See, in this fraction here, the denominator is an irrational number. Root 3 is irrational. It's a surd because 3 is not a perfect square. So when we rationalize the denominator, we want to change this bottom number to a rational number. But I can't just change it to whatever I want without changing the value of the fraction. What I really want to do is I want to find another fraction that has the same value as this but has a rational number on the bottom. So the thing is, if I times the bottom by root 3, it will become rational because root 3 times root 3 is just 3. Any integer is a rational number. So you know, if I don't want to change the value of a fraction, what I do to the bottom, I must also do to the top. So because I times the bottom by root 3, so too I times the top by root 3. So here, this number in blue, this number in red, they are equal. They have the same value, they'd occupy the same position on the number line, but this one has a rational denominator. Okay, that particular example didn't involve expansions at all, but sometimes you'll get a fraction that's a little more complicated to rationalize its denominator. So we're going to do the same sort of thing here. We want to times top and bottom by something. So I don't change the value of the fraction, but I change the denominator to something rational. So here we're actually going to use expanding brackets. Here we can use the rule a minus b times a plus b equals a squared minus b squared. This is called the difference of two squares rule. Now you might be thinking, what the hell does this have to do here? The point is, I need to think of something by which I can multiply this to make it rational. This rule actually really helps. See, the point is, if I times the bottom by root 3 plus 1, so here if you like a is like root 3, b is 1, if I times these two together, I'll get a rational number. Because this rule up here says if you have a minus b times a plus b, all you do when you're expanding it is you just square the first, so root 3 squared is 3. Square the second, so 1 squared is 1, and stick a minus between them. As in the first example, if you times the bottom by something, you must also times the top by it. So I have 7 times root 3 plus 1. So I need to times 7 by the whole shebang here. So it's like I have brackets around here. So I go 7 times root 3, 7 times positive 1. Of course, the bottom, 3 minus 1, is just 2. So it turns out this number and this number are equal, but this one has a rational denominator. It's not at all obvious from looking at them that they're equal. That's why we need a sophisticated rule like this. So let's use this rule again to rationalize the denominator here. So I want to times the bottom by something that'll make it rational. Well, because of the difference of two squares rule, because of this expansion rule, I know that I can just times it by root 2 minus root 6. Because if I have a plus b times a minus b, when I expand it, I just square the first, root 2 squared, I square the second, root 6 squared, and I stick a minus between them. Once again, what you do to the bottom, you must also do to the top. Essentially, I'm timesing this fraction by 1, which means I'm not changing its value. So I have to times 5 by everything. So I have to times 5 by root 2 and 5 by root 6. Okay, and of course the bottom 2 minus 6 is just negative 4. So it's 5 root 2 minus 5 root 6 over negative 4. But it just looks a bit weird to have a negative there. So I could simplify this even further by timesing top and bottom by negative 1. If I times this top by negative 1, I'm actually just going to switch the order. So I'm going to end up getting 5 root 6 minus 5 root 2 over 4. See, all of these fractions here are the same. They have the same value, same position on the number line, but you can see that these ones here have a rational denominator and this one is considered simplified. All right, let's now look at some harder questions. So let's say that x equals root 3 plus root 10. We are going to go and calculate that number squared, cubed, and multiplied by 4. So here is the quick way, if you've forgotten, for a perfect binomial square. If you have a plus b all squared, what you do is you square the first, you square the second, and it's always positive, squares always are. And in the middle of that, though, this is the one people often forget, you have to put 2 times a times b. So you square the first, square the second, and in the middle is 2 times the first thing times the second thing. So if I want to calculate x squared, I need to take root 3 plus root 10 and square it. I square the first, which is 3. I square the second, which is 10. Now, in the middle goes 2 times root 3 times root 10. And you know that root 3 times root 10 is root 30. When you're multiplying two surds, you just multiply the numbers under the surds. Of course, I can simplify this further because 3 plus 10 is 13. So I'm left with 13 plus 2 root 30. Now I actually can't simplify root 30 any further. There is no perfect square that's a factor of 30 other than 1. So I leave it like that. All right, so what would be x cubed? Well, I could just take x, which is root 3 plus root 10, and multiply it by x squared. Of course, you know x times x squared equals x cubed from index laws. Okay, so now what we're doing is using FOIL, which you would have already learned. When you have a binomial expansion like this, you need to multiply everything in the first bracket by everything in the second bracket. FOIL just helps you keep track. So the F means I multiply what comes first in each bracket. So root 3 times 13, I'll just write as 13 root 3. Then O, what is on the outside of each bracket. So root 3 times root 30 is root 90. We can simplify that later. Then we have I, the thing that is inside each bracket. So root 10 times 13. And then the L in FOIL is what is last in each bracket. So root 10 times root 30 is actually root 300. So it turns out I can simplify a few of these. Root 90 is root 9 times root 10. So it's 3 root 10. I can't simplify root 10 any further because 10 is not divisible by a perfect square other than 1. It turns out, however, 300 is. So the highest perfect square that goes into 300 is actually 100. So I end up with root 100, which is 10 times root 3. All right, simplifying this, 13 root 3 plus 10 root 3, and then 3 root 10 plus 13 root 10. Now I have x to the power of 3. What about x to the power of 4? Well, I could just multiply this here by x. Another way I can do it is I can take x squared, which was this, and I can square it. So remember, the quick way to square is you square the first, square the second. So 2 root 30 squared is 2 squared, which is 4, times root 30 squared, which is 30. Now in the middle, I have to go 2 times this times this. So 2 times 13 is 26, times 2 is 52. So it'll be 52 root 30. Of course, 169 plus 120 is 289. So x to the power of 4 is 289 plus 52 root 30, and we're done. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.